Good morning, everyone. Hope everyone is well. The third topic that we're going to cover in the permutation and combination unit is actually a lesson called Permutations. It is very much like the fundamental counting principle. We're actually going to use everything that we covered in the fundamental counting principle lesson and the factorial lesson. Before we start and look at a definition of permutation, can you do me a favor and again write up at the top in nice and bold letters, how many choices do I have? So remember that pervasive question that we often asked ourselves is how many choices do we have at each stage? Okay, let's take a look at the definition. A permutation is an arrangement of objects in a definite order. And that word order is of uber importance. You have to follow a certain order. Okay, do me a favor, and for the next few examples, can you just draw a little division line? Because I'm going to show you two different ways to attack the example. We're going to start with our traditional way, and then I'm going to introduce you to a new way. So let's think about our first example. How many different ways can I line 7 students up at the front of the class? And if we were together in the classroom, what I would do at this point is I would ask 7 people to stand up. So envision 7 people standing up. And they'd be standing out in the audience right now in the classroom. And I would say to the rest of the class, okay, I'm going to call them one at a time up to the front. So I would say, take a look at the 7 people, everyone. How many choices do I have available to me for my first call? Then maybe I'd call somebody up to the front. How many choices do I have for my second call? And I'd call that second person up to the front. How many choices for my third call? And I'd call that third person up to the front. How many choices for my fourth call? How many choices for my fifth call? How many choices for my sixth call? And then what we'd see at this particular point is we'd see 6 people standing up at the front, up at the podium with me, and we'd see one final person waiting to get the call. 7 times 6 times 5 times 4 times 3 times 2 times 1, everybody knows is also 7 factorial, or 5,040. Okay, let's take a look at the second example. How many different ways can I line 5 students up at the front if I'm still choosing from the group of 7? So again, at this particular point, I would ask the 7 people, they're back at their seats now, I would ask the 7 people to stand up for me again. And I would say to the class, okay, I'm going to call up 5 of them. How many choices do I have available to me? Look at the people standing up. How many choices do I have available? How many choices do I have available? Now I've got 2 people standing up at the front with me and the others still standing out in the class. How many choices? How many choices? And how many choices? 7 times 6 times 5 times 4 times 3? 2,520. What would have happened in this particular situation, 7 people would have originally been standing up out in the audience. 5 would have ended up at the front with me at the podium, and 2 would have remained standing up in the audience because they didn't get called. I didn't need all 7 of them like I did in the first example. Classic fundamental counting principles, classic permutation questions. Let's take a little look at what we've got here. It says these are permutations since students are being arranged in a definite order. The notation is as follows. And again, this is going to be our second formula that we have completely and utterly memorized. So we have the factorial formula, n factorial, and now we're going to have the permutation formula. So let's take a look at the left side. The capital P represents the permutation. N represents the total number of objects. So in both of our examples, that was 7. I had 7 people that I was working with. R represents the number of objects being arranged. So in the first example, all 7 of the people were being arranged. In the second example, only 5 were being arranged. Equals n factorial, total number of objects, factorial, divided by n minus r, total minus arranged, factorial. Okay, let's take a second and redo our first 2 examples using the permutation formula. So in my first example, my n is 7 and my r is 7. I arranged all of them. They all came up to the front. In my second example, my n is 7 and my r is 5. That's the difference. Only 5 of them came up to the front. 2 of them were left standing in the audience. Okay, first example. It's a permutation of 7, choose 7. That's how we say that. Permutation of 7, choose 7. The formula reads n factorial over n minus r factorial. So n is 7 and r is 7. N factorial. N minus r finds me with a 0 factorial, and now we know that 0 factorial was one of our special rules. 7 factorial, 5040. 0 factorial was 1. Answer, 5040. Visual way, formula way, exact same answer. Take a look at the second example. I'm dealing with a permutation of 7 people and only choosing 5. So it's a permutation of 7, choose 5. 7 people in the audience choosing 5 to come up to the front. N factorial, n being 7. N minus r factorial, n being 7, r being 5. Leaves me with 7 factorial over 2 factorial. 7 factorial is 5040. We know that from before. Divided by 2, 2520. Same answer, visual, formula, perfect. Okay, let's take a look at a couple more examples. There are 8 songs to be arranged for a concert. How many different ways can they be arranged to form the concert program? So Miss Bordage is going to put on a concert for the school, and her and the choir decide that they're going to perform 8 songs. So they can't agree on how the 8 songs are going to be performed, the order in which they're going to be performed. Everybody's arguing and they can't decide on it. So Miss Bordage says, hey, let's write the name of the songs that we're going to perform. Let's put them in the basket. And when we get up to perform, I'll just pull them out one at a time. And that's the order that we'll perform them. So here are my 2, 3, 4, 5, 6, 7. Here are my 8 songs on the pieces of paper. The concert starts. Miss Bordage puts her hand into the basket. How many choices does she have for the first song? How many choices does she have left? How many choices does she have? How many choices? Choices, choices, choices. And for their very last song, we can envision it, there's only one piece of paper left in the basket. So 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 8 factorial, 40,320 possible different arrangements with the 8 songs for their concert. Now, if we look at this from a formula perspective, total number of songs would be 8. Total number of songs arranged or performed would also be 8. They're performing everything in the basket. So it's a permutation of 8. Choose 8. Formula says n factorial all over n minus r factorial. 8 factorial over 0 factorial. We know 0 factorial is one of our special rules. 8 factorial, 40,320. Okay, let's look at something a little bit more difficult. A club of 9 students wants a president and a vice president. How many ways can this be done? So here's the analogy. Ms. Staples and I want to start a data management club at Notre Dame. We call a meeting and 9 people show up to the meeting. 9 students show up to the meeting. And we say to them, listen, we'd prefer to have a president and a vice president for some of the activities and some of the extra roles of responsibility and whatnot. Everybody raises their hand and says that they're interested in those positions. Why? They probably want to put them on their resume. So Ms. Staples and I can't choose. We have 9 fantastic kids. They're all wonderful. We can't choose who we want to be the vice president and the president. Well, we decide then that we're going to put all 9 of their names into a bowl. We're going to hold a meeting and we're going to choose randomly. So we come into the meeting. Ms. Staples puts her hand in the bowl. She's swishing her hand around. There are 9 pieces of paper or 9 choices for the role of president. She picks, she reads out the name, takes the paper, throws it in the recycle, puts her hand back in the bowl, and now we have 8 choices for the vice president. 72 possible presidents and vice president options for this question. Now, how would I do it via formula? Well, my N, my total number of interested parties, is 9. My 2 represents the total number of objects to be arranged. I only have 2 positions of authority, president and vice president. So it's a permutation of 9 choose 2, n factorial over n minus r factorial, 9 factorial over 2 factorial, or I'm sorry, 9 minus 2, 7 factorial. So sorry guys, that's my mistake. Sorry. N is 9, R is 2, leaving me 7 factorial. Now we could either do this on our calculator or just as a little refresher, 9, 8, 7, 6, 5, 4, 3, 2, 1. Over 7, 6, 5, 4, 3, 2, 1. Remember from our factorial lesson? Cancel, cancel, 9 times 8, 72. Same answer, visual way, formula way. If you don't mind, let's flip to example 4 or example 5, please. Okay, we're going to get into a few higher end concepts now. It says, let's arrange the letters in the word math. A letters question is the classic question for a permutation on the test. And we've done some letter questions already. We've done a question with NICE, N-I-C-E. We've done a question with Fathom, F-A-T-H-O-M, where, you know, you put all the letters, wooden blocks in a cloth bag, you shake them up, and you pull them out one at a time, asking that pervasive question, how many choices do I have? Okay. So let's take a look at this. I've got the letters for the word math. How many different words can you make? I've got 4 letters. I put them in a cloth bag, shake, shake, shake. When my hand goes in for that very first pull, I can feel 4 blocks in the bag. I pull one out. I display it on my desk. Hand goes back in. I've got 3 letters or 3 choices available to me. I pull it out. I put it on the desk. Hand goes back in the bag. I've got 2 choices. And finally, 1 choice. Very straightforward, very, very easy type of question. So my N is 4 letters. And my R, I'm going to arrange all 4. So it's a permutation of 4. Choose 4. 4 factorial over n minus r factorial. 4 factorial over 0 factorial is 4 factorial, or 24. Very straightforward. Now, let's change it up a bit. How many different words can you make if A has to be in the second position? So a stipulation is being made, a specific instruction is being made that A has to sit in the second position. So let me give you an analogy on how I tend to explain this to you guys. We've all been students for a long time. Everybody in our classroom has been students for a long time. And everybody's aware of what we like to call the annoying child. The one that's talking all the time, the one that's on their cell phone all the time, the one that, you know, kind of is not doing what they're supposed to. So the classic response to the annoying child is that the teacher moves where they sit and they're forced to sit up at the front near the teacher. So they lose their choice of where they're going to sit. That option is taken away from them and they're told, you're sitting right here and you're not allowed to move. So this is the very, very same situation. The A is being told where to sit. So the A is being completely taken out of the shake, shake, shake bag because their position is already known. They're sitting where they have to sit. That means that when I go to put my hand in the cloth bag and the letters are floating around, I've got 3 choices available to me for the first position, the M, the T, and the H. 2 choices for this second position, and 1 choice for the final. So again, the A is being told where to sit. Now, with the formula, because the A is not even being put in the bag, my total number of objects is 3, and my number of objects being arranged is also 3. So it's a permutation of 3 choose 3. 3 factorial over n minus r factorial. 3 factorial over 0 factorial. 3 factorial equals 6. So this whole idea of specifically telling someone or something where they have to sit, the annoying child concept, it's very, very common in this particular unit. Okay, let's keep going. How many different words can be made if the T and the H have to stay together? This is another important word in this unit, the word together. So what do I mean by that? Okay, let me give you an analogy on this. Again, we've all been in school for a long time, and everybody is sort of familiar with what I like to call the annoying boyfriend and girlfriend. So the annoying boyfriend and girlfriend are the boyfriend and girlfriend that are together all the time. They're in the halls together, they sit together at the caf, they sit together in class. They're glued at the hip, as you'd like to say. Okay? So they are almost considered like one unit, okay? Because where T goes, H is also going. Similar to if you're going to a party and you invite your friend, you know he or she is inviting the annoying boyfriend and girlfriend. So instead of these two being considered two different options, they're not. They're one option. Now, let me explain it to you from the cloth bag example. I put the 4 letters in the bag. Unbeknownst to me, the T and the H have a magnet in the center of the wooden block. So when I go to put my hand in the bag for the pull, the T and the H have now stuck together. They're considered one particular block because they've got magnets. So how many choices do I have available? 3. The M, the A, the big TH. How many choices do I have available? I pull something out, put it on the desk. 2 and 1. Now, is my question finished? No. There's an extra part to this type of question. Let's go back to the boyfriend and girlfriend. Annoying boyfriend and girlfriend are in our class. I'm standing at the door waiting to start class. I see annoying boyfriend and girlfriend coming down the hall. I say hi to them, they say hi to me, and just as they get to the door, annoying boyfriend stands back and allows his girlfriend to walk in first. He's the true gentleman. He allows his girlfriend to walk in first. Let's run the scenario again. Standing at the doorway, I see annoying boyfriend and girlfriend coming down the hall. They say hi to me, I say hi to them. Just as they get to the door, annoying boyfriend, who isn't a true gentleman, walks into the classroom first and allows girlfriend to walk in after him. So what I'm saying is order matters. It could have been TH or it could have been HT. So I have to compensate for that and multiply the 6 by a 2 factorial because of the whole idea of order. Again, annoying boyfriend could have been a gentleman and let his girlfriend walk in first and then him. Or he could have not been a gentleman, walked in before her, and let her walk in after. Again, this is a permutation of 3 choose 3. So 3 factorial over 0 factorial gives me 3 factorial, but I still have to multiply it by the 2 factorial in order to compensate for the order in which the letters fall. Okay, let's take a look now at question 6. A salad bar has 7 salads to be arranged in an order. I always pretend we're at the Mandarin with this one. If the Caesar salad has to go first, and the potato salad has to go last, how many different ways can the salad bar be arranged? So with this one, I always pick a student and I pretend that they work at the Mandarin, and I joke around and say that they are in charge of the salads. And that the first night that they go into work, their boss tells them that when you put out the 7 salads, I want Caesar going first, and I want potato going last. For whatever reason, that's what the boss says, and that's what you're going to do. So, without saying, this is the annoying boyfriend and girlfriend, or this is the annoying child concept. Because the annoying child Caesar is being told where to sit, and the annoying child potato is being told where to sit, so they don't have any options. They're not in the mix of the other salads moving around. So instead of having 7 salads, I actually have 5 salads that are moving. The other ones know exactly where they're sitting. So how many choices? How many choices? How many choices? And how many choices? 5 factorial, 120. So very, very much like the A example. Exactly. And again, this would be a permutation of 5. Choose 5. And the reason is that the 2 other salads, they're not in the mix. They can't move. They're being told where to sit. So 5 factorial over n minus r factorial, 5 factorial over 0 factorial, 5 factorial, 120. Okay. If the 3 pasta salads need to be side by side, how many different arrangements can there be? Okay, hold on. Let me draw this out. I've got 7 salads. And the 3 pasta salads need to be together. I'm kind of thinking that this is like annoying boyfriend and girlfriend. So my student that works at the Mandarin goes to work that night, and he or she is told, yep, I want you to put out the salads, and the only rule is that I want you to put the 3 pasta salads together. So instead of it being a permutation of 7, it's actually, this block is considered 1. So it's no longer a permutation of 7, it's a permutation of 1, 2, 3, 4, 5. So how many choices do I have? 5, 4, 3, 2, 1. But the part that I've forgotten about in that is that inside this little grouping of 3 pasta salads is also a mini permutation, similar to what we had with the T and the H. Order matters. So inside this grouping of pasta salads, I also have a permutation of how many choices for the first pasta salad? 3. How many choices for the second pasta salad? 2. How many choices for the third pasta salad? 1. So this is a classic 5 factorial for all of the salads times a 3 factorial for the pasta salads? 120 times 6, 720. So it's a permutation inside of a permutation. It's a permutation inside of a permutation with the 3 pasta salads. Now, again, from a formula perspective, this is an n of 5. 1, 2, 3, 4, 5. And you're arranging all 5. So it's a permutation of 5, choose 5. All multiplied by 3 factorial. The 3 factorial representing the arrangement of the 3 pasta salads. Think about it. If I had, penne, fusilli, and rotini, it could go penne, fusilli, rotini. It could go penne, rotini, fusilli. It could go rotini, penne, fusilli. So within the arrangements of the salads, the pasta arrangement could end up being 3 factorial for a beautiful 720. Okay, I think there's one other example that I'd really like to try to get to because it's a letter example. And if you don't mind, let's scoot to number 11. Please and thank you. Okay, so we're scooting from 6 all the way to 11. In how many ways can all the letters in the word education be arranged? So hold on, let me just count. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 letters. If there are no restrictions. So that means that I'm not telling anybody where they have to sit. I'm not telling anybody that, certain letters have to be together. I'm not telling anybody anything. So that means how many choices? 9, 8, 7, 6, 5, 4, 3, 2, 1. I'd be pulling 1 letter out of the cloth bag at a time and displaying them on my desk. Okay, very standard. How many ways can all of the letters in the word education be arranged if the word must start with a D and it must end with a T? So this is very much annoying child. D is being told where to sit. T is being told where to sit. So they can't move. That means that I have 1, 2, 3, 4, 5, 6, 7 movable objects. So if I've got 7 movable objects, it's changed from a 9 factorial question to a 7 factorial question. Okay, let's make it a little bit harder. How many ways can all the letters in the word education be arranged if the word must start with a vowel and end with a consonant? Vowels. Consonant. Okay, let's think about this. Vowels. Vowels are E, U, A, I, and O. those are all vowels. So there's 5 different choices. Consonants would be, the D would be a consonant, the C would be a consonant, the T would be a consonant, and the N would be the consonant. So notice I'm filling in the first position. How many choices do I have available? I've got 5. How many choices do I have available for consonant? I have 4. And now when you're filling in the remainder, don't forget, one of these 9 letters is sitting in the first position. Maybe it's an A. I don't know. One of these 9 letters is sitting in the last position. Maybe it's an N. So how many movable objects do I have left after those 2 positions are filled? 1, 2, 3, 4, 5, 6, 7. 7, 6, 5, 4, 3, 2, and 1. 5 times 7 times 6 times 5 times 4 times 3 times 2 times 1 times a final 4, 100,800. Put a star beside that one. That one also often catches people on the test. Okay, final example. How many different ways can the letters in the word education be arranged if the E and the D must be adjacent? The word adjacent is just another fancy way of saying together. So if I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 letters, and the E and the D have to be together, this is the annoying boyfriend and girlfriend concept. So in this concept, I've gone from a 9 factorial question, all of the letters being considered individual items, to 1, 2, 3, 4, 5, 6, 7, 8. Remember, the E and the D have to be together. They're considered one option. So 8, 7, 6, 5 choices, 4 choices, 3 choices, 2 choices, 1 choice. And then please, 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 don't forget that when the E and the D are together, they could be ED, boyfriend allows girlfriend to walk in before him, or DE, boyfriend walks in first and then allows girlfriend. This is order. So 8 factorial times 2 factorial, 40,320 times 2, 80,640. Thank you again for a great lesson. Talk to you soon.